The world is moving towards a renewable future. Solar, wind, and nuclear are getting cheaper, and batteries are getting more efficient, and electric cars are getting popular. But what about electric planes? Even a regional airliner can spray 300 tons of carbon dioxide for a short trip, and there are hundreds of these flying above you right now. Fortunately, enthusiasm for them is increasing as well. DHL, the global logistics giant, has ordered 12 electric cargo planes, while United Airlines has ordered 150 passenger electric planes and intends to go all electric by the year 2050. Almost all major airlines are putting significant emphasis on decarbonizing air travel, not only because of the hefty penalties and carbon tax, but also for the many possibilities electric planes have to offer. A plane burning jet fuel costs $1,000 to $2,000 per hour, while an electric flight consumes $4 to $6 at most. This is ridiculously low. Electric motors are going to use propellers as opposed to super noisy jet engines. In fact, the noise levels of these propellers is just 60 decibels for some of the small electric aircraft. That's lower than a normal conversation. The propellers also have an efficiency of 85% compared to less than 40% for jet engines. Fewer moving parts in propellers also means lower maintenance cost and high reliability. In fact, electric planes were pretty popular in the early 20th century with lead-acid batteries and eventually nickel-cadmium batteries. So what exactly prevented them from getting the mainstream attention as the jet engines did? To put it simply, it's the laws of physics. You see, unlike electric cars, the weight and volume of the fuel matters far more in airplanes. If the fuel source is heavy, the plane needs more lift to take off, which in turn means more fuel, which, if heavy, makes it even heavier. And this cycle continues, making it virtually impossible to take off. So we need an energy-dense fuel so that it's lightweight and low volume. In fact, this is a major deciding factor for all aviation fuels. We can measure this quantity using energy density and specific energy of the fuels. Energy density, that is energy per unit volume, is given on the y-axis, and specific energy, which is energy per unit mass, is on the x-axis. We want both of these quantities to be as high as possible because we want the fuel to be lightweight and low volume. Gasoline and jet fuels are right over here with an energy density of 43 megajoules per kg. Others like ethanol, methanol and natural gas are somewhere here. But batteries? Well, they're all the way over here, less than 2% of the energy density of the jet fuel. For cars, energy density matters much less. Moreover, electric motors are far more efficient than internal combustion engines, and that makes up for this loss to some extent, and at least it makes it feasible to produce electric cars. But for electric planes, the laws of physics themselves make it impossible, even to create a prototype jet airliner. Almost all electric planes in development so far are small planes, either 2, 9 or 20 passenger planes. It is easy to see why. It not only makes it technically feasible, but also easy to get past the hefty regulations of the aviation industry. Energy density of the fuel matters less and less as the size of the plane decreases. In fact, it becomes more economical to have small electric planes as opposed to internal combustion engine planes. This is why all drones are entirely electric. DHL has ordered 9 passenger electric planes, which have a battery weight of 3,500 kilograms, which is about 40% of the weight of the empty aircraft. This is not as bad as the Airbus A320 we discussed earlier. However, Wright Electric has built 2-seater electric planes with a battery weight of just 270 kilograms. This is even less. So we can see that there are some thresholds above which it is impossible to create airplanes with batteries. It takes 2000 watt-hours per kg energy density fuel to make it technically feasible to electrify an Airbus A320. To electrify a small regional airliner with just 50 to 80 passengers, it takes at least a battery capacity of 500 watt-hours per kg. The most advanced lithium-ion batteries currently have an energy density of just 275 watt-hours per kg. Fortunately, all is not lost. We do have some hopes for future aviation fuels. Lithium-sulfur batteries have an energy density of 490 watt-hours per kg. So they can power regional flights, in fact much cheaper than jet fuels. The only constraints they are facing is durability. The anode of these batteries deteriorate rapidly due to charge and discharge cycles, and scientists are tackling this with nanotechnology and better materials. Another hope is hydrogen. It has 3 times the specific energy of jet fuel, but it also has 4 times the volume. Hydrogen is a highly volatile gas, and we can't really store them in the wings like jet fuel. We need to store it in the fuselage, but this would increase the size of the fuselage, increasing the aerodynamic drag. But hydrogen is also much lighter than jet fuel, so it is basically a trade-off between higher aerodynamic drag versus lower weight, and it depends on the size of the airplane how these factors weigh in. In addition, creating hydrogen from electrolysis of water is also quite inefficient. Using energy to generate hydrogen using electrolysis, transporting it and using it in hydrogen fuel cell is inefficient use of energy compared to directly charging batteries using electricity. So it does hold immense promise as a future aviation fuel, but it has many hurdles to overcome. Electrification of aviation is inevitable, but so far the challenges are numerous and tricky. Nonetheless, research projects all around the world are giving confidence that some fuel source must emerge as the future of sustainable aviation.